Have you ever planned a perfect sunny picnic, only to have the forecast switch to rain at the last minute? It is a common frustration we all share. We rely on weather forecasts for everything, choosing our daily outfits, planning major events. When the prediction changes, it can feel like the forecasters are just guessing. But there is a complex and fascinating science behind predicting the weather. It involves powerful tools, immense calculations, and a deep understanding of our planet's atmosphere. This video will pull back the curtain on how forecasts are really made, why they change, and how you can use them more effectively in your daily life. Understanding the weather is crucial for agriculture, transportation, and public safety. A good forecast can save lives by warning about dangerous storms. A bad one can lead to significant disruptions. The process begins with gathering a snapshot of the current state of the atmosphere all around the globe. This is a monumental task, requiring a network of advanced technologies working together around the clock. The atmosphere is a chaotic, constantly moving system. Small changes ripple into big differences later. So, how do scientists turn this chaos into a useful daily forecast? Observation, computation, and human expertise working in harmony. To forecast the future, we must first get an accurate picture of the present. Our most powerful tools for this job are weather satellites, tirelessly orbiting high above the Earth, our planet's dedicated photographers. They provide a bird's-eye view impossible from the ground. Massive hurricanes, cloud systems sweeping continents, storms before landfall. There are two main types of weather satellites, each with a specific job. Geostationary satellites orbit about 22,000 miles above the equator, matching Earth's rotation to hover over one region continuously. Polar orbiting satellites fly lower, around 500 miles up, scanning the globe in strips as Earth spins. Detailed snapshots twice a day. Satellites do more than take pictures. Infrared instruments measure temperatures in the ocean and atmosphere. Microwave sensors measure water vapor, a key ingredient for rain and snow. Combined, they build a comprehensive 3D picture of what the atmosphere is doing right now. This initial snapshot is the starting block for every forecast. While satellites give the grand overview, we also need detailed measurements within the atmosphere. Thousands of automated stations measure temperature, pressure, wind, humidity, and rainfall. Twice a day worldwide, weather balloons carry radiosondes up to the stratosphere, profiling temperature, pressure, humidity, and winds at many altitudes. Over oceans, buoys and ships report air and sea temperatures, wave heights, and winds. Thousands of aircraft add data from cruising altitudes. All this information is collected in near real time and sent to processing centers to assemble a complete map of the current weather, the initial conditions. Once we know what the weather is doing right now, the next step is to predict what it will do next. Numerical weather prediction models are complex computer programs running on the world's most powerful supercomputers. They apply the laws of physics and fluid dynamics on a giant 3D grid. Imagine graph paper wrapped around Earth, each tiny box holding temperature, pressure, wind, and humidity. The model advances in small time steps, computing how air moves between boxes, how sun warms the ground, how evaporation forms clouds, and how pressure differences create wind. Repeating this millions of times builds the forecast hour by hour. A single run can involve trillions of calculations and still take hours to finish. Finer grids capture small thunderstorms, but halving box size can demand roughly 10 times more computing power. That's why agencies invest in supercomputing, from the American GFS to the European ECMWF, among others. If all models use the same physics, why don't they always produce the same forecast? In a complex system, tiny changes in starting conditions can create huge differences later. The famous butterfly effect. We can't measure every point, especially over oceans, deserts, and polar regions. So models fill gaps with data assimilation, and different centers use different techniques. Many small processes, a single cloud, a raindrop, wind over mountains, are too small for the grid. Models approximate them with parameterizations, and these choices differ. Small starting differences plus different approximations make forecasts drift apart, especially farther out. Day 3, Day 5, Day 7. In the first 24 hours, models usually agree because errors haven't had time to grow. Let's make this concrete with a common real-world example. Imagine you live in a coastal city. It is Monday morning. You are planning a big family barbecue for the upcoming Saturday. You check your favorite weather app. It shows a bright, sunny icon for Saturday, with a high of 75 degrees. The forecast, based on model runs from Sunday night, looks perfect. High pressure over your region. Now fast forward to Wednesday. Offshore, a small low has formed, barely noticeable on Monday's sparse ocean data. New satellite images and a report from a passing ship capture it more clearly. Models are rerun with the new data. The computers start crunching, and the calculation changes. The American model pulls it toward your coast. Rainy, windy Saturday. The European model tracks it farther north. Mostly clouds for your city. On Wednesday, your app updates. Now a 40% chance of rain. By Friday morning, the storm is much closer. Satellites, radar, and buoys feed precise data, and the models come into better agreement. They now show a direct hit. The forecast updates to a 90% chance of heavy rain and wind. Your sunny picnic becomes a rainy washout. Not because forecasters were wrong on Monday, but because science improved as new information arrived. That's how it can change. Given that small errors can lead to big forecast changes, how can meteorologists convey confidence? A single model run shows only one possible future. Enter ensemble forecasting. Instead of one run, the model runs dozens of times, each with tiny tweaks to the starting data. One member might warm the ocean slightly, another strengthens winds over mountains. Small perturbations representing uncertainty, the butterfly effect in action. Run them all, and you get a diverse family of 20, 30, even 50 forecasts. If all 50 members show a storm passing north, confidence is high. Likely a dry day. If 35 members show rain and 15 show dry, uncertainty is higher. Forecasters issue a nuanced probability, a 70% chance of rain. Those graphics that look like noodles are spaghetti plots. Each noodle is one member's track. Tight bundles mean higher certainty. Wide spreads mean lower certainty. First, check the forecast frequently, especially as plans get closer. Monday's guideline becomes Friday's reliable action plan. Second, a 40% chance of rain doesn't mean 40% of the day. It means in 10 similar setups, it rains about 4 times. It's a statement of risk. Use percentages to decide. A 20% shower chance might not stop a walk. An 80% thunderstorm chance should change a hike. Third, use reliable sources. National weather agencies and broadcast meteorologists. They interpret raw models, understand local biases, and add human expertise. Finally, look beyond the icon. Hourly details reveal timing, wind direction, and temperature trends. That detail can leave your morning and evening plans unaffected, giving you a far more practical picture. The science of weather forecasting is a story of constant progress. A 7-day forecast today is as accurate as a 3-day forecast was 30 years ago, thanks to better observations, more powerful computers, and more sophisticated models. New satellites, denser ground sensors, even cars and homes, and faster supercomputers will enable storm-scale modeling that pinpoints severe weather with greater precision. Ultimately, forecasting blends raw computing power with human intelligence. Forecasters interpret models, weigh ensembles, and communicate risks. So the next time your forecast changes, remember the incredible journey of that prediction. It is not a sign of failure, but a sign that science is working with the best possible information to give you the clearest possible view ahead. If this helped you read forecasts like a pro, tap like, subscribe, and share. Check back before your plans, and pack the umbrella when the odds say so.